Okay, so last time, as you know, we already have started with the finite element method. And I just want to summarize. So what we currently consider is this partial differential equation, which is a model for electrostatics, even for magnetostatics, when we can describe the magnetic field by a scalar potential U. Otherwise, U would be the electric scalar potential. The thermal field in a static case, U would be the temperature T. A potential flow, U would be psi, the scalar flow potential. So we see we have a second spatial derivative. Important again is, please realize that you have a material parameter depending on space. And it's not easy, for example, when you apply the finite difference method here, because you also have the divergence operator operating on this material parameter. We want to get the solution U in the whole computational domain we define. In order to get a unique solution, we need on the whole boundary, we need boundary conditions. Standard boundary conditions is that you prescribe your physical quantity, for example, electric potential, as we know, along an electrode. We call this a Dirichlet boundary condition, and this E means essential. Essential in the context of finite element method, because this is a boundary condition we have to apply also after we turn over this partial differential equation to a weak formulation. On the other hand, you could have a flux boundary condition, which we call a Neumann boundary condition. However, this N is not really for Neumann, although it is mathematical speaking a Neumann boundary condition, an inhomogeneous Neumann boundary condition. It is within the context of finite elements a natural boundary condition, because this boundary condition we will be able to incorporate in the weak formulation. Okay, so this was the starting point, and then we already derived by help of the divergence theorem and the so-called test function V, we were able to turn over to this weak formulation. And here you see that we now look for a solution which still has to fulfill this Dirichlet boundary condition and this whole integral equation we have here. And what do we have gained? First of all, since we already know our boundary condition, the Dirichlet boundary condition, we set the test function V at the Dirichlet boundary to 0. So V equal to 0. We already know the solution by putting the test function. The test function is some help function for us. We are not interested in the test function, but it helps us in this sense, as we have seen, due to the integration by parts, which means the application of the divergence theorem, that we were able to incorporate this Neumann boundary condition, which we have here. Furthermore, very importantly, a mistake in the slides, I have forgotten there the material parameter, but we have it now on the slides. This material parameter, depending on space, is now free from any derivation, very important. And the last point we have gained is that the order of the derivative of the unknown U is reduced. As you can see here, we just have a first order spatial derivative. In most cases, we are also not able to solve now this weak formulation. Anyway, we have gained these 3 points. That is very importantly that you realize this, which was not the case for the finite difference method. And you even can show then when you discretize, because in most cases we get also no analytical solution for the weak formulation. When we now go the next step, meaning discretizing computational domain, making some ansatz for the unknown U, that we get a numerical solution, you can even then prove that you get the best possible numerical solution, which does not mean it's the most efficient method. Most efficient for us engineers means that you get in the smallest computational time a solution which is most accurate. Yeah? In some cases, especially waves, electromagnetic waves, you have rectangular structures, perhaps the finite difference method is more efficient. But it's the most general method and gives the best approximation you ever can achieve. So these are very nice properties. Okay, now, since we cannot solve this weak formulation for general setups analytically, we go and now do similar steps, but being different again from the finite difference method. So first of all, we have to do a space discretization. So as you can see here, we have a computational domain, very simple domain in 2D here, and we subdivide this domain in finite elements. In our case, we do a triangulation, so we have triangular elements. And at all these nodes, which we have here, we call them finite element nodes. At these nodes, we don't know the solution. At some nodes, we know the solution already because these are the nodes where we have the Dirichlet boundary condition. But please remember that those nodes where we have incorporated here the Neumann boundary condition, we know the normal derivative scaled with the material parameter, but not the physical quantity itself. So also those nodes where we know the Neumann boundary are unknowns. Okay, now we discretize this domain in 2D quadrilaterals or triangles, in 3D all the bunches of geometric elements starting from debts up to hexahedral elements or pyramids, whatever you want. There we all, for all these elements, we have a machinery how we can approximate, and that is the case, can approximate the physical quantity. We also will approximate the test function. So you see the continuous test function is now a discrete one. This H parameter also will tell you that we have done a space discretization. So H is actually a characteristic size of each finite element you have there. So the length of, let's say, the smallest edges you have, the smallest edge you have in your computational domain. So this would be, for example, something like this. So this is then H. Okay, and you see, we do a very interesting ansatz. We do a sum of so-called basis functions. So these are our basis functions. And as you can see, the basis function depend on the space. Yeah? And that is scaled with a coefficient. The coefficient will be a constant, but clearly different in each finite element method where we have our physical quantity unknown. And we do quite the same for our unknown u. It's now also a discrete unknown because we somehow sample in space and at all the finite element nodes. We now make such an ansatz again with the same basis function, just another index. And here we also clearly have the coefficients, and that are the coefficients we want to compute in all the nodes where we don't know our physical quantity. Yeah, that's clearly in all the nodes where we do not have any Dirichlet boundary condition. Yeah, so these are our unknowns at the finite element nodes. And now, I guess it's clear for you, when you make such a simple ansatz with a sum, yeah, that we have to force this property, the property of local support. Yeah, we call this local support. That means this basis function is the exact one at the node where it corresponds as a basis function. As you can see here, this is NA, this is the node A, so it is equal to 1. And then it's clear if you evaluate this sum, since it is 0 at all the neighboring nodes, not only these nodes, also all the other nodes in the computational domain, what you get out for the approximation is then exactly UA. Yeah, because for B equal A, this will be 1. For all other indices of B, it will be 0. And so the sum gives you really exactly at the node A, the value UA. And therefore, it is allowed to make such an ansatz with a sum. Otherwise, you would have a mixing how you can then again separate your solution and get the solution of a physical quantity, for example, electric scalar potential, at all our finite element nodes. So you see, this is the key point, let's say. And the rest, what we are doing is some rearrangement of terms, and then clearly we need some tricky methods how we can efficiently implement this method on a computer. Okay, so that means we have our weak formulation, which is still the continuous one. Now we will substitute this approximation for the test function, this approximation for the unknown physical quantity u. Yeah, and then we should get out a discrete system of equations. So as you can see here, for simplicity, because always inhomogeneous Dirichlet boundary condition needs some tricks how you do it. So let's do it for simplicity. There is just one additional point. I don't know, this was a copy and paste. So we assume that at all the nodes where we have a Dirichlet boundary condition, it is 0. Mechanically speaking, you fix there your cantilever or whatever. Or electrically speaking, for electric scalar potential, there you have grounded the electron. Okay, and now you see what we actually have. We have this long form. We still have our integral over the computational domain. We have substituted here our continuous test function by this ansatz, the discrete ansatz. The same for the unknown physical quantity u. Yeah, and on the right-hand side, we know we have the integral over the natural boundary where we have prescribed our flux, physical flux, Qn, and this is the approximation for the test function. The only thing what you in addition see here now, it is just a sum from 1 to the number of equations. EQ is equations, clearly, because we select out some nodes on the boundary where the Dirichlet boundary condition is prescribed, in our case simply u equals 0. Okay, now what can we do? Very importantly, we can rearrange by the following sense. Since VE is a constant, you can put it not only in front of the sum or in front of the nabla operator, you can even put it in front of the integral. Yeah? Actually, we would have to apply here the product rule. But since VA is a constant, at the discrete nodes, you can put it out of the integral. The same you can put for UP. Yeah? UP is also a constant at all the different nodes. So what remains then is, and you always can interchange a sum and the integral. So I also put the sum in front here and this sum also in front here. Okay, so that means, as you can see, we have now the discrete form. The discrete form means you have your first sum. And that is the sum over A, where A is the index for the test function, which is also a constant at all the individual nodes. And then we combine, as you can see here, in the sum going over B, this volume integral and this surface integral. Yeah? And since I have put here the right-hand side to the left-hand side, close the parentheses here, and this has to be equal to 0. So this is now a nice form, because what we can do is we can set VA to V1. Yeah? And all other V2, V3, and so on, we set 0. That's free for us. That means you get the first line of an equation, and you can divide by V1, because we are not interested in V1, but we still have the sum here over the P's for all the unknowns. Oh, something is missed here. Terrible. Here is missing my unknowns UA. Ah, not UA, UP. UP. Okay, so you get for all the UPs, your unknowns, one equation. You fix the test function coefficient VA to V1, and then you can divide by V. And then you fix VP to V2 for the next node. Yeah? And you get again an equation. And so on, as long as you have number of equations, you always can divide by this coefficient of the test function. We assume it is different from 0, otherwise it makes no sense, because multiplying with 0, 0 with 0 is fulfilled, but we want to get the equations for the unknowns UP. That means we get then for each of this test function coefficient equation with number of equation unknowns for UP, but we get number of equations for all these UP. And that you can collect in a matrix and you simply write it by a system matrix, collecting all the unknowns of your physical quantity in a vector U is equal to the right-hand side vector. Clearly the right-hand side vector will give us here, will be given here by the NA scaled with the fluxes you have along the Neumann boundary. So you see, we already have now our system of equations, which we just have to solve, and then we get a solution vector U collecting all the solution at all the nodes, finite element nodes, where we have not known before our physical quantity U, scalar electric potential, for example. Okay, so this is everything. Yeah. However, implementation will not be feasible in this sense. So I will give you some ideas for the implementation. I hope you accept that you will not understand everything, but we have own courses for it, or you just look up in one of the finite element books, and clearly I will always recommend my finite element book. But there are also other books on the market you can look for. Okay, but you see, that was the procedure. So the procedure was going from the strong form to the weak form. They are totally equivalent, no approximation. And then you do a space discretization, and you do an ansatz, an approximative ansatz again, yeah, because we have this sign here. It's an approximation for the test function and for the unknown. This you substitute, you rearrange, and then you see, very nice, we get rid of the coefficients of the test function because we are not interested in this coefficient, and we get number of equations for all the unknowns U at all the nodes. Yeah, and that we can solve, and we have our solution. And I don't prove it here. Anyway, I tell you that with this ansatz, you call it a Galerkin approximation, you get the best approximation you ever can get. That you can prove mathematically. So now going in some details, it's clear. Let's have a look. The system matrix has a lot of entries. It depends how large your mesh is, how many nodes you have in your computational mesh. But each entry at the position AB, yeah, is computed via this volume integral. Yeah. You have to evaluate there your material parameter nu. You have to evaluate there the gradient of the basis function. Well, we don't know currently how the basis function looks like. Anyway, we will have HUD functions as we had in 1D. And I have made here something, yeah, like this. So it is a special function being 1 at the node going 0 to the neighboring nodes and clearly to all the other nodes in your computational domain. And the gradient of NP is just the same as NA, it is just for another node, because you get then the entries for A and B at the specific position of your system matrix at A and B. Yeah, and the right-hand side is more or less the same. It's even easier. It is a vector. You just have to evaluate your basis function at all the nodes when you integrate over the surface gamma n and scale it with your flux. Well, what you see, we have to do it for all indices A and B for all the nodes where we have an equation. However, that is perhaps not very efficiently, because you see we have two basis functions, NA and B. So if this is NA and NB is something at this node, we don't have any overlap. So we compute a lot of entries which are just 0. We just have an overlap if NB belongs to one of these nodes. So let's make it green. To this node, this node, this node, and this node. NB overlap with NA. Yeah, all the other entries you can compute. Yeah, it's up to you, but it's not efficiently for implementation because you just will get out the 0. That also tells us, and that is the important point, since these hard functions have a local support, they are just different from 0 in a small region, that you have a sparse system matrix. Yeah? So you have a lot of 0 entries. You will never store the 0 entries. You will always just store the non-zero entries. And the second thing is also what you can nicely see. You have a gradient on NA, you have a gradient on NB. If you exchange NA with NB, you get out the same. Yeah? So you have a symmetric system matrix. Yeah? That also means you will just store the diagonal and let's say the upper entries different from 0 of the whole sparse matrix. Yeah? That is very important that we have a symmetric system matrix. That doesn't depend on the method, it depends on your partial differential equation. There are also partial differential equations. That is not the weak form, it is the strong form where you have, for example, a convective term and they will be inherent non-symmetric. Okay, then we have to solve all the non-zero entries. Here we get the symmetric sparse matrix. Yeah? So we even can reduce. And that is important if you have 10 million, 20, 30 million of unknowns. That's a standard in computation. It makes a difference if you store all the non-zero or just the diagonal and the other non-zero entries of diagonal being above the diagonal. Okay, so we have learned quite a lot, yeah, how we can make it efficient. Still, I have not told you how you compute the basis function, but what we have seen, it doesn't make sense to evaluate this interval for one entry over the whole computational domain omega. So let's make the trick as we always can do without approximation. You use already the subdivision of your computational domain by the finite elements, and therefore you have here now the sum over all finite elements, and you just integrate over the element domain. Yeah? Each of the triangles or quadrilaterals or dots you have, and you have to evaluate clearly the same term within the integral. Yeah? That will help us in such a sense that you will always compute an element matrix. This is the small k. And you see the difference is just here. You just integrate over the element. And here you will never differ if this is an element where you also include directly boundary or not. You always compute this element matrix. Yeah? If it is a triangle, it's a 3 by 3 element matrix. You have 3 nodes. Yeah? In each of the nodes, you have a basis function and NA and B. yeah, you see it is now P and Q are the indices, and they go to the number of element nodes. So this is the number of element nodes. Yeah? So it is not the number of equation, it's the number of element nodes. Yeah? And I make it here, for example, 3 by 3 for a triangle. Okay, and instead of the sum, we have this assembly operator. Yeah? And the assembly operator now looks for each entry of this element matrix where we have to put it to the global system matrix. And now this assembly operator needs the information if there are some directly nodes. Yeah? And then there will be no assembly. And just for those where we really have an equation, it will put to the correct position of the system matrix. Okay, so you see, in this sense, we have now broken it down to the element matrix. And now we will look how to evaluate this element matrix efficiently. That is the key point. Since you see, we need a lot of steps until we get our system matrix. Quite different for the finite difference method. It was very simple. We just put this finite difference stencil to our partial differential equation, and computing the entries of the system matrix, as we have seen, is quite simple. Okay, so still, yeah, what is the problem? Still a problem. Yeah, each finite element has a different shape. Okay. So the integration is quite complicated if you have different shapes of the triangles or quadrilaterals or whatever you have. It would be good to have a reference element, and there we look at the integration points within the reference element to make it very efficiently and hopefully without any error. Yeah, okay, you can do it analytically, but makes no sense. You will see with very low order of integration point, you even make it exact. And still we don't know how to compute this basis function. And that would be a nightmare because you have to compute it every time new for each new shape of your finite element. And if you go back and look here at our computational domain, well, each triangle has more or less a different shape. So this will be a nightmare. Makes no sense. Yeah? And that is why we go to the concept of a reference element. That means each finite element having any shape in your computational domain will be mapped to a reference element. And this is this mapping. I will show you just the idea for a quadrilateral, but the same for triangles or in 3D hexahedra, that's whatever. Because if we come up to a reference element, then this, as you see here in the so-called unit space, it always has the same shape. So we just have to do in a pre-computation, compute there where are the optimal integration points, because we will do a numerical integration. And we can pre-compute our basis function. Yeah? And everything is resolved. But we have to do this mapping. Yeah, and the mapping concept is, I would not say easy, but the idea is as follows. This is the standard finite element method. You will also call it isoparametric elements. So you will also use the same basis function as you will then use for the approximation of the physical quantity, also for this mapping. So you see, I have again, now I just call it Ni. We have 4 nodes, therefore I is going from 1 to 4. Yeah, the quadrilateral has 4 nodes. Yeah, clearly also in the physical space. But they will be somewhere in the xy or xyz coordinate space in 3D. And you make also these ansatz that, as we can see here, the nodes of our reference element they always will take on the value plus minus 1, yeah, as we can see here. Yeah? So it is a rectangular element going from -1 to +1 for xi and -1 to +1 for eta. Okay. And now you can say, okay, we have to find the basis function, sometimes called shape function or interpolation function, in such a case that we can evaluate the global x coordinate at any position xi eta by this ansatz here. Yeah? And this xie means this is really for the element e, the global x coordinate for node 1, node 2, node 3, node 4. Yeah, and what we can do is now, for example, we can make such a approximation, and for a quadrilateral, it will be a bilinear function. So you can have any constant plus a alpha 1 psi I plus a alpha 2 eta I, and that is the bilinear function. Alpha 3 psi I eta I. Yeah? So this psi I eta I, yeah, we have here. We also know in the physical space xi. Yeah? And now we have 4 equations because we have 4 nodes. And we make this ansatz here. And we have 4 unknowns, alpha 0, alpha 1, alpha 2, alpha 3. 4 equations, 4 unknowns, consistent. We just solve it and we will get out our basis function ni. The same we do for y. We do a different ansatz, perhaps with coefficients beta 0, beta 1, beta 2, beta 3. But you will see, you will get out the same coefficients. Alpha 0 will be the same as beta 0 and so on. Okay, that means I don't do the derivation. You will get out at the end for a quadrilateral, the same you can do for the others. Yeah? If we have a triangle, we will just have 3 unknowns because we have 3 nodes. So we just can make an ansatz for a linear function. Yeah? So there will be not such a bilinear term. Yeah? So if you put this away, this would be the ansatz for a triangle because we just have 3 nodes. And as you can see here, this is the general solution. You even can combine it and don't write n1, n2, n3, and 4. You can make it with the index I. And you see we also have this index I for xi I and eta I, and they are a function of xi and eta. And we know xi I, eta I takes on the values plus minus 1, as we have here in our unit space. Yeah, so that would be a nice job for evening. Have a beer and just make it by hand or use MATLAB and put it there, and you know, MATLAB solving then a 4x4 system will be very easily done, or you do it by hand, a Gauss elimination, whatever. Okay, so you see we get now this mapping between the physical space and the unit space. And this mapping is the key point, yeah, because that means what do we have to do? We have to evaluate such an integral. So we will transform the global nabla operator, being a nabla operator with respect to x, y, and z in 3D. We will transform it to a nabla operator for the unit space. Yeah? For this, we have to do the transformation. We will transform the integral, which is the integral over the physical space x, y, z. We will transform to the unit space. Yeah? We know how to transform integrals, at least for 1D. Yeah? The extension to 2D or 3D is using the Jacobian matrix. Okay. Now you have a machinery how to compute this basis function. But the machinery we will always just have for this unit space. You don't have a machinery, you always have to do it if just a little bit the shape of the quadrilateral or the triangle changes in the physical space, you again have to recompute them. Makes no sense. So make the mapping to the unit space. And you see, in this sense, for example, here would be for this node, yeah, the basis function, it's exact one at this basis function and goes to 0 for all the other nodes. Here, perhaps you see it even better for this node. It's exactly 1, and it goes to 0 to all the other 3 nodes. Yeah? So the property has to be fulfilled. Otherwise, we have made the mistake. Yeah? Okay, but that has to be fulfilled, yeah, because when I want to evaluate the global coordinate x for this node, yeah, 2, which is in unit space this node 2, I evaluate it for xi equal -1, eta equal 1, and then clearly I want to get out xi here, this, which is x2. Otherwise, again, this ansatz with a sum makes no sense. So you see, also in this simple case for these 4 nodes, this basis function or shape functions, interpolation functions we compute by this ansatz need this local support. And that is given here. You just can make this plot in MATLAB or Python or wherever you do. Okay. And as I have told you, you call these isoparametric elements because these mapping basis functions Ni we will also now use because they have this local support also used for the approximation of the unknown physical quantity U. Okay, so now we have this machinery, and now we should go in some details how we really evaluate, how we do this transformation, which we have to do for the term in the integral, so that we really can integrate over the unit space over our reference element as shown here. Yeah, and that is on this slide, which is a little bit abstract. Yeah, therefore we will go in some details. But perhaps you know, when you make a change of variables, that we also do when we have to solve sometimes integrals. Yeah? We change the variables because with this transformation, we then get, let's say, some integral where we have then this analytic solution. Yeah? We get it simpler and know, okay, how to solve it. But for this, you ever know, when you do change of variables, then the global integration over x, y, and z is a local integration scaled by the determinant of the Jacobian. Yeah, that is the same as you have in 1D. In 1D, the Jacobian matrix is a 1-by-1 matrix. But if you have a two-dimensional integral and you do a transformation of your variables, yeah, then we already have a 2-by-2 matrix. The more complicated thing is, actually, we know we have the nabla operator with derivatives with respect to x, y, and z. And that we somehow have to substitute by this nabla operator with respect to our reference coordinates, because we have a reference element, and that would be xi, eta, and 2d, and the third coordinate you call theta in a three-dimensional space. And what is in between is the Jacobian Transpose. Now, the Jacobian Transposed is actually what you do is a product rule. Yeah? You do a derivative with respect to xi, but xi depends on x. Yeah? Xi now as a vector meaning xi, eta, theta. Yeah? The local coordinates depend on the global, and also the global depend on the local. So what you do is a product rule. You do the derivative of the global with respect to the local, and then you have this one. Okay, now how to do a derivative of a vector with respect to a vector? You ever have seen it? In mathematics, you have once Okay, no problem. We do it. Okay, so as you have seen, we have something like this. We have the derivative of x with respect to psi. Yeah, I write here x, as we know. Let's make it in 2D. Yeah, in 3D is just the extension. Yeah, it's a little bit faster. Yeah, and psi is the position vector in our reference element is psi and eta. And for this, yeah, we always should go and look up in the book. Wikipedia is also quite nice. Or what I always recommend to make it without a mistake, go to index notation. Yeah, we have a vector with two indices. Yeah, so I can say also in this, so now index notation. I can write x as the first coordinate, the second coordinate. Yeah, so x1 would be x, x2 would be y, x3 would be z. Yeah, and the same we do for psi, psi1, psi2. It's just easier. Yeah. Okay, so what we write here is we do the derivative of xi. I is going from 1 to 2 in 2D or 1 to 3 in 3D with respect to psi j. Yeah, and now I guess it is clear. What you have to do is you have to fix I to 1. Then you get the first row of your matrix. Yeah? Then you have dx1 with respect to d psi1. And the second entry here on the position 1, 2 would be dx1 d eta. Sorry. Clearly d eta, but we have index d psi 2. Yeah. And then you get the second row. You fix I equal to, I is going from 1 to 2 in 2D. So we have dx2 with respect to d psi 1. J is going from 1 to 2. And then d psi 2 to d. Yeah. And that perhaps I also can rewrite as dx d psi dy dy dx d eta dy d psi dy d eta. So I just go back because we are somehow used to x, y, and z and xi, eta, and zeta in 3D. Yeah? So you see the extension to 3D, I would say, is simple. We have just a further index. It's going from 1 to 2 to 3. Okay. So, and if we now go back, we realize that this is not really the Jacobian, but it's the Jacobian transport. Okay. Yeah, because perhaps should also write here explicitly x is a function of psi and eta, make it 2D, and y is a function of psi and eta. On the other hand, I also can write psi is a function of x and y, and eta is clearly also a function x and y. Yeah? So because they are interrelated, that was our mapping ansatz as we have seen. And clearly we cannot compute these derivatives, so the gradient of the basis functions with respect to the global coordinates. That's not possible, yeah, because we just have our basis function on the local coordinates of our unit cube, which is psi, eta, and 3D. We also have theta. Okay, So now you exactly see this problem here. I have the global derivative of n I and nj depending on the local coordinates on the unit cube, integrating over the x, y, z space of our physical element. But now we do the transformation, and as we have seen, instead of using the gradient with respect to the physical space x, y, z, we use it by the Jacobian, yeah, because we just have to bring this Jacobian on this side, yeah, and then it would be the transpose and taking the inverse as you have it exactly here. And I have now the gradient operator with respect to psi and eta in 2D. Yeah? And the same we have here. And don't forget the integration now, also this substitution, yeah? What we also have to do. And now everything is fine. Yeah? Because now with this transformation of the integral, we really integrate over the unit space, yeah, over our reference element, which is quite simple in our case of this rectangular element. From psi is going from -1 to +1, yeah, as you can see here, -1 to +1, and eta the same from -1 to +1. Yeah? And for such a nice element, we use Gauss quadrature, and it will turn out, without any proof, that this will be the numerical integration point. And they are exactly ±1 over square root of 3. And this will be exact for our problem. So it's nice. We don't have to do the burden of analytical integration. Huh? And we make no numerical error. Okay. So a lot of information, I guess, and I don't expect that you understand all details. For this, it will take really time. And from my point of view, to really understand a finite element method, you have to code your own simulation program, let's say in MATLAB or Python, so that you don't have to do everything. Yeah? Okay, if you're interested, you can also implement the algebraic solver, solving your algebraic system of equation, but the main point is not solving the system of equation. The main point is all this transformation. So as we have seen, exactly the main point at the end is two things. One, to compute this element matrix. We have seen we do all these steps we just have discussed, and this assembly operator. These are the two main steps to really need to understand. For this course here, I don't expect that you understand all the details. What I expect that you really know the big difference between finite element method and finite difference method, and what are the main steps. Yeah, not that you are able to do the implementation. Okay. Yeah. To see this now also explicitly, I have made this slide because I think that makes sense. What you can see here is again what I have told you. So the global physical coordinate x depends on the local coordinates, and it is made by these answers. Yeah? And I is going from 1 to the number of element nodes, and the same it is for this. Yeah. So we can do this chain rule if you have any function, and the function was for us what is the integrand, and you take a derivative with respect to psi, and you have in your mind that psi depends on x and y. You can do first a derivative of f with respect to x, and then the inner derivative of x with respect to psi, plus, as you know from this product rule, the derivative of f with respect to y and y with respect to psi. Yeah, and the same is when you do the derivative with respect to eta, you have a similar term here. Now, you can rewrite this as an equation with a matrix as shown here. So we have here the derivative of f with respect to psi and f with respect to eta. So this is just written now as a vector. Here, we take all the derivatives of x and y with respect to psi and eta in this matrix here and multiply it with the derivatives of x and y as the derivative, of f with respect to x and f with respect to y in this matrix. And then we see that what we have here is a nabla operator with respect to the local coordinates and the nabla operator with respect to the physical space, the global coordinates as we call it. Yeah, and in between is the Jacobian transpose. If you now look as back, then you see you have x with respect to psi and y with respect to psi. If we go back, and hopefully we have made no mistake, so you have x with respect to psi and x with respect to eta. So it is just a transpose. Yeah, what we have formally done before. Okay, so that gives you this extremely powerful machinery to make the finite element method feasible for implementation. Yeah. So we break down to reference elements. For this, in advance, we know where are the optimal integration points. We know in advance the basis function. However, don't forget that this Jacobian, yeah, depends on the global coordinates. So you have to evaluate this for each integration point. That makes some computational effort. Okay, anyway, you have a machinery now for implementation, not easy to understand. I think it needs 2-3 times go over the slides to see the idea of the implementation. Okay, now if we go back to our example, then you get a very nice result. It's more or less the same result. So if you use this linear or bilinear basis function and this finite difference of second order, as we have discussed, and you use the same computational mesh, you should exactly get out the same numerical result. So on this case, it's the same. That is why because we have no deformed elements. Yeah, we have all these nice rectangular elements where you can apply this simple 5-point stencil for the finite difference method, and there you will really get out the same solution. If you evaluate now along this center line, yeah, it's the center line, then you get out here the electric potential, which should be 2, because here we had the electrode with potential 2 volt prescribed. At this electrode, it was 0 prescribed. So perhaps that you remember here, V was equal 2. Here V was equal 0. Here V was up there it is. Okay. Anyway, and here V equal 2. So you see, it exactly starts at 2 volt and ends at 10 volt. Otherwise, we have made a mistake, yeah, because there we have prescribed the directly boundary condition. And you see, it first goes a little bit down. It's clear because it has to go through this narrow slit where we also have electrodes potential equal to 0. And then it has to go up again to 10 volt because at this electrode we've prescribed 10 volt. Okay, so you can make a nice plot in your post processor and play a little bit around. As you know, we are not only interested in the potential field, we are clearly interested in the electric field. Now, for the electric field, the solution looks like this. you know that the electric field on a continuous level is minus gradient of the scalar potential. So in the context of finite element methods, you will compute this for each finite element in the center of your reference element, which will be also the center of your physical element. And this value you map with one color, and that is why you see these staircases we have there. Yeah, you can smooth it, but you don't will improve the accuracy. So what you could also do is to evaluate it in each integration point of the reference element, and then try to find the integration point in your physical element, which is the inverse mapping, and the inverse mapping will be nonlinear, or at least for quadrilaterals already. And that is also because now if you look, yeah, and again evaluate it along this line here, here is the electric field. Here is the electric field over the position. Yeah, that was a distance of 200 meters. And you see these staircase lines we have here. Yeah? Okay, so you can use higher order basis functions, then you cannot do this bilinear ansatz. Yeah? So you also have to take some alpha 4 psi squared plus alpha 5 plus alpha 5 eta squared and so on. So you can make any polynomial here with any order. That's up to you. It will be just more involved in the computation, but that you always just do once for the reference element. We always do it just for the reference element. So the main point is, as I have told you, is this mapping. Yeah, and that what we have here, this Jacobian, that takes time. Yeah, that takes time to be evaluated, and that's why, in general, clearly the finite element method will not be as fast as the finite difference method. But don't forget, you can discretize any geometry, at least with stats in 3D, which is not possible with the finite difference method. Okay, so if you are interested in any details, there is a book on the market in Springer, already 3rd edition. You can look there. Or even better, I invite you, there is the course by Thomas Bauernfeind. It's the starting course at ICTE for numerical simulation. And then there are 2 additional courses, multiphysical simulation 1 and 2, always with exercises. And you will also learn there not only electromagnetic fields, also thermal fields, mechanical fields, acoustic fields, and their couplings. So really multi-physics in this part. And we will go to more details clearly as we have done today to understand the details of the finite element method. But I guess you have got the impression how the machinery is working, what is the theoretical idea, and then which machinery we need for computer implementation. And at least what you have seen, we have a lot of steps to do until we get our system matrix. Yeah? Not the case for the finite difference method. Are there any questions or comments? So the finite element method is really the method of choice for any physical field. What I have told you is the continuous Galerkin approach. There's also a discontinuous Galerkin approach, especially if you have to solve conservation equations. We also have conservation equation, but mostly we rearrange them and get the second order partial differential equation for the scalar electric potential or for the magnetic vector potential and so on. So for conservation equation, you will need some additional ideas, which are the so-called discontinuous Galerkin methods. or you use finite volume methods, which is a standard for flow dynamics. But in computational mechanics, structural mechanics, in acoustics, in electromagnetics, and so on, the standard method is the finite element.